Okay, everyone, welcome back to our statistics class notes here in section 9.2. This is the last page in section 9.2, page 143. And I want to give you a little brief introduction to what's called the t-statistic. So we will not be able to use a z-score for when we're looking at the sample means. Okay, so like we did when we were looking at sample proportions, we realized that because it was approximately normal, we could use a z-score. So there's a lot of mathematics behind this why we cannot use a z-score. We're going to have to use something, or a z-statistic. We're going to have to use something called a t-statistic, which is it's very similar to a normal z-score, a z-statistic, but it's a slightly different thing. So I'm just giving you a brief introduction to it right here on the last page, and we'll see much more of this in sections 9.3 and 9.4. So hypothesis tests and confidence intervals for testing and estimating the mean of a population are based on a statistic called the t-statistic. So it has the following form. T is equal to x bar minus mu divided by s divided by square root of n. So this is an estimation of the standard error, right? Because the standard error would be sigma divided by square root of n. So s is the sample standard deviation. So this is a standard error estimate. Okay, now it's very similar looking to what doing a z-score. The problem is it does not follow the normal distribution because the denominator changes with every sample size. So the t-statistic is more variable than the z-statistic, which we learned about last chapter when testing for population proportions, whose denominator is always the same. Recall the z-statistic standard error was this, right? Standard error equals p naught times 1 minus p naught divided by n. So the problem here is that this guy is not going to quite follow a normal distribution where this guy did. Okay, so if the three conditions for using the central limit theorem for means hold, the t-statistic follows a distribution called the t-distribution, which is still symmetric and bell-shaped. So I'm showing a t-distribution here. This one right here that's got a taller peak and thinner tails is the normal distribution with a mean of 0, standard deviation of 1. So that's the z distribution, the z-scores, where we get our z-statistics from. Notice that the tails really, after 3 standard deviations to the left or right of the mean, get almost close to 0. Almost 99.7% of the stuff is in here. However, with the t-distribution, it's a little more spread out. The tails are thicker. Okay, so there's going to be more area out in the tails. This has a shape that depends on what we're going to call the degrees of freedom, and I'll explain that much more later. This one right here, I'm given just a degree of freedom of 1, but you'll understand the degrees of freedom in the next chapter. I just want you to know that the shape will depend on something we're calling degrees of freedom. And if the degrees of freedom is small, the tails are thick. And as the degrees of freedom increases, the tails get thinner. And degrees of freedom will increase the same way that the sample size increases. So we'll spend more time on this in the next couple of sections of chapter 9, but I just wanted to give you an introduction that we're not going to be able to use a z-statistic. We're going to have to use a t-statistic, and that t-statistic will follow a t-distribution, not the normal distribution.